Okay, so welcome everyone to this week's grad student symposium. We have a math student with us today, Sam, who was nice enough to give a talk today. It's going to be about loss and recovery. And so, yeah, I've never even thought about this kind of stuff, so I'm excited to hear about it. And yeah, please go ahead.
Thank you for the introduction, and thanks to the organizers for having me. I'm going to talk about the story of loss and recovery. So let's get started. This story is, in fact, also serves to act as a grand addition in this series. So this is a Taken series. It's a film from 2008, and I didn't want to spoil it, but the poster itself pretty much gives it. So there's this local government expert who is trained and has a bunch of skills to protect and prevent weird things from happening, and his own daughter sets out on an adventure outside, so in Europe somewhere. And now she gets taken, and now his job is to basically take the takers down and get her back. So this is a kind of loss and recovery that they show in this film. And my plan is going to be proposal to add this as the next one in the series. So we're going to have the daughter not just go to Europe on a music festival visit or whatever, but instead we're going to have her explore the depths of the universe and just go into a black hole. And so then the father here is named Bob and the daughter is named Alice, is supposed to come back together. So the job for us is to kind of look at how we can recover the daughter from this kind of setting. So I guess this makes more sense for the dialogue here, because even though he says, I don't know who you are, I don't know what you want, and whatever, I'll take you down. It's more applicable in the sense of a black hole, right? Because at least here he knows there's a human who's talking on the phone. Here it's like, okay, this is where you could really apply the setting of, I don't know, I really don't know who you are. Now you could ask me why is such a setting necessary, because we already have information loss and recovery in usual quantum channels. So any communication system involving message transmission, even classically, has some sort of noise, and so there's some loss happening. And the literature, in fact, is filled with all these Alice and Bob things. So another thing to ask maybe, so I'd like to have questions on the go as well. So this is an example of a question you could be asking. Hey, so why did you take this this particular film and not any other film? And the answer is actually in the heading. It's action, right? You know, everyone is bored of rom-coms, binge watching in the quarantine. So all this Alice and Bob story where Alice is like being told something by Bob, and his message just gets lost is the usual setup for a rom-com. But now we can actually change it in the setting of a black hole, in which case you'll actually need to work around and get some action. Another reason is that there's another famous line from the film which says that he has this particular set of skills which he's going to apply, and I think that's a good role model for us. Even for me as an international student, I've just learned some bunch of local techniques. And in a new setting like this, we need to use our same set of skills, but apply these in this global setting, right? So that's a good role model to have. Okay, so this is the usual channel mode, and you could, even though the talk is supposed to be about encoding and decoding in black holes, we can always use the kind of skills or techniques we learn in our usual communication channels. So this leads to quantum cryptographic protocols. Okay, so I'd like to first explore some of the information theoretic side to this in the sense that if if there is a way possible to encode everything in terms of symbols. So that's a very general question. And for that, I shall use another string. Hopefully this is okay. Yeah. So the kind of messages we are going to explore is supposed to be something that is very difficult to encode, right? And the usual expression in the form of language takes up symbols. So, for example, the sentence can always be divided into parts where there's an object and then there's an action. Similarly, we have the corresponding things in physics. We have particles and then there are fields that encode the interaction between them. So an example is for, let's say I want to say this, I experience an apple falling towards the earth, and that's what I encode. So there's two objects which are going to have distinct positions, and then the falls towards is what acts as the interaction between these two objects. So that now the question is it really possible to encode or just express everything that is experienced in this sort of language, or is there inherently some loss even before any noise comes in? The point is exactly the statement that I started with. So let me try to highlight why this kind of statement is a statement which doesn't encode the actual intention that was there behind it. And the logic behind this, so this has been studied in terms of logic, that if there is a sentence S of the form, this sentence is false, then if S is assumed to be true, then the fact is then S is this whole thing. So I can replace it here, and then this sentence is false becomes true, but then this sentence is S itself, so it's not compatible with the initial claim that S is supposed to be true. So this is where if Alice sends in, or even Bob sends in a message saying this, it's not clear what is meant. Is it meant to be stating that the sentence is true, or is it meant to be stating that the sentence is false? On the other hand, the same dilemma happens if you assume S to be false, then this sentence is not false. And hence this sentence, which is S itself, is true. So this is again not compatible with the original claim that is meant to be. So this is just based on logic. There's no interference with any eavesdropper or an environment channel. And we already get sentences which are not clear enough. So in terms of symbols, how can we look at what is the key operation over here? So the fact is that there's a self-negation of its own state, which means that we are looking for a sentence of the form, this sentence is not expressible, and that means that two of the symbols in the sentence must encode what it means to say not and what it means to say expressible. So let's assume that we have these two symbols to do that. Then the rest of it is the sub-sentence which is left. And you could self-reflect on this sub-sentence in order to get the whole sentence. So this is the only way to refer to the entire sentence back. If there was anything else placed in this box, which is not self-reflecting, then the statement would have referred to something else, which is a subpart of the statement and not the whole sentence in itself. So the only way to get the whole sentence back is to have symmetry in outside, in what is stated outside and what is stated inside. And hence this is a mirror or a reflection operator, which you need to have such kind of sentence. And so in this setting, if outside and inside are symmetric, then this is the statement which encodes what was meant in English by this sentence. So this is actually a 4. I mean, not even 4, but okay, we can argue on whether it is 5 or 4, but essentially just within 4 or 5 symbols, there is a expression or a string of these 4 or 5 symbols, which says that basically I am not expressible. And so this sentence is totally outside of the things that we can express. And this is in fact the basis for 1931 Gödel's incompleteness theorem. which sort of builds on this in terms of arithmetic. So here I encoded these in terms of symbols, but what he has to do is for an arithmetic system, he has to do a Gödel numbering, which basically encodes this statement exactly in the form of numbers. Okay. Any question at this point? I should maybe stop for questions because the rest of the talk will sort of build on exactly this point. So we are trying to see if everything can be encoded in language, and we found out that, oh, if you have a mirror operator which does this sort of self-reflection, then you turn out that you can get things that are lost, that don't stay within its own system. Okay, so now now that I've stated arithmetic, let me talk about numbers again. So if you look at the this in terms of a statement of number versus its reflection in the sense of a negative number. So usually this would have been written as A and A inverse. Then what it tries to express is that identity, which would be formed if you had minus A acting along with plus A, is not expressible. So if this was a philosophy talk, maybe I would have explored this line further, but that's the most that I'm going to do at the symbolic level. So let's go to numbers. Again, another reason why I took that film was because now you can take n to be a symmetry. So there's a bunch of numbers which are going to act as local parts, just similar to the blue colored sub-sentence that we had. And then we want to go to a global self based on such a symmetry. So the natural setting for this is what happens in induction. You could have started with numbers over here that are, say, you start with the number 1, and then you have a statement S, which expresses something that it relates to the number 2. And then there could be another version in which you start with 2, and then another statement for 2, which will lead you to 3. But then there could be 3, and then another statement which leads you to 4. If there is a symmetry, which is what algebraically is studied, so it goes beyond this level of individual parts, then you can do a loss of these particular numbers. So maybe I should zoom in and look at only this part first, which means that you have a clear notion of what these individual parts are. But if you allow loss to happen, which is sort of zooming out, then although technically you are losing information granularity, the good thing is now you have a symmetrical picture for all those things. So you can have many things at the same time. So instead of looking at this sub level, you go to a global level and then prove or state this sentence for in the form any number n relates to n plus 1 in some particular way. And then if you have stated this, finally you can come back to the usual numbers by just substituting for a particular number n plus 1. Right. So this is what works as the prototype for induction. And this is the starting point for arithmetic local to global correspondence. Okay, so that's at the level of numbers. So what happens if you extend this to R? So if you extend this to real numbers, what you get, I agree. I should have made like this in a bunch of more steps, taking one dimension and Euclidean spaces first, giving the usual Stokes theorem. But I'm going to skip it in the interest of time because it's a physics talk. So here is what Stokes-Cartan theorem does, exactly similar to what happened for natural numbers, except now it's going to work for real numbers. And in fact, you can this statement in fact works for manifold setting as well. So you can take a manifold and take a differential form of it on it. And then one way is to go about integrating it. So there's multiple levels of loss and recovery happening, which are color coded over here. So above, I just had two levels, but now here there's a level of loss and recovery within the objects that you have and the maps. So there's two operators, one which takes the integral, but it takes the integral after taking the differential form, after taking the exterior derivative on the differential form. So this is, I've stated it a bit in reverse for just symmetry purposes, but this is to be read as d omega. And on the other hand, there is a lift of this in the global form. So you can do this on the whole manifold itself. And what you get is this partial derivative sign, which means that you go towards the boundary of the manifold. So this is loss, but then you have this as a recovery. So then this total thing is one loss followed by a recovery. And here you have an addition first and then some loss. So it's the reverse. But the fact is that this diagram commutes. So these two actually match up. So this one version is an integration on the boundary of the manifold versus this is the integration on a bulk. And so this is generally used in many forms, let's say divergence theorem or any kind of integral equations to its differential formulations. So this is another boundary to bulk correspondence that I had started with. So in terms of physics, what you want to think is that there are some local parts which we understand. So let's say one theory is quantum physics, another theory is gravity. And now there's a global kind of picture in which you want to patch these together. So another prototype of this is in fact the expression of this exact theorem in the form of a duality of the de Rham cohomology with homology of chains. So essentially the proof of this also turns out that all these local parts are going to have reflections of each other cancelling out. So this is again another form of stating identity is not expressible, but in a very in a very concrete sense, not in symbols, but in terms of vector fields. And so because these form chains, these parts cancel out and you never see these. So the local parts are all going to be patched up very smoothly to form this global thing. And this is exactly what gets you from the left-hand side equation to the right-hand side of the equation. Okay, so we started with only symbols in language. We did it for arithmetic, which is natural numbers. It sort of went through algebra. We have now stated it for real numbers. The next thing to do for this boundary to bulk correspondence is take C, that is the complex plane. And just as de Rham cohomology was there previously, now we have something called Dolbeck cohomology. And there's an exact expression of this by Grothendieck's lemma, which starts with this. So this is the usual Cauchy integral representation of a function in complex analysis. But now you also have this extra term, and this is sort of what you would have if you only wanted to consider this boundary. So every time I'm talking about some local or a boundary part, it's going to be in blue versus whenever we are trying to go to a bulk. So this is the whole of the interior. It's going to be in purple. Okay, so this integral is actually acting in the bulk, and you could sort of see why dimensionally at least this sort of matches, because you had f initially, but now you have taken a partial derivative. And then you have added it back up. So that sort of matches it. Okay, so then you can define another function g in such a way so that if alpha is taken to be f dz bar, then you get alpha to actually be the del bar of g. And this is a quick computation you can check. All of this is set up for the actual lemma, which goes as the follows. If alpha is if alpha is something which will after the operation of del bar go to 0, then in fact you can check that there is a boundary term coming from if you started from APQ, you can go one dimension below sort of to PQ minus 1, And this is in fact for Cn. It's not even just one complex plane. It's a complex in n dimensions. So there's this boundary term which you can find out whose del bar will actually give alpha. So there's another boundary to bulk correspondence that is formed here. Okay, so these are essentially covering all of the math side that I wanted to talk about. As you've gone from symbols to numbers to real numbers to complex planes. Before I go to Hilbert spaces and maybe even operators on Hilbert spaces, maybe I should stop or and even see if there are any questions. Okay, so let me continue. Back to the slides. So we say we talked about arithmetic, we've talked about real numbers, we've talked about complex numbers. In fact, I didn't mention a really interesting case of Riemann-Hilbert problem because it sort of was covered in the previous talk on holography. And it's in fact really important in terms of our department as well, because a lot of work in the math department happens over here. Starting with the references, I'll just mention the references quickly if anyone wants to look up these things. So Goldberg-Segal theory is in fact going to be the basis for most of the results following this. And then Professor Dino Beck from the math department is another person who has worked on this and is well known for this particular paper on the distribution of length of longest increasing subsequence of random permutations. So what happens in the Riemann-Hilbert problem is similar to the Cauchy formulation. Given a boundary, given some conditions on the boundary, we want to uncover the bulk. And so these two, again, Professor Peter Miller, again from our department, have worked on sort of randomizing these matrices and working out on ensemble or averaging out solutions for these things. Okay, so maybe I should also mention something about the Riemann sphere in case anyone is interested. And both of them have given like amazing courses in this past year. So if anyone is registering still, please go ahead. Okay, so instead of just looking at the complex plane, what you can do is add one point at the infinite, add one point at infinity, and what you get is a Riemann sphere. Then given any contour, you can form two regions. One is going to be the plus region, which is the region bounded inside. And then there's going to be a minus region, which goes towards infinity. So in this Riemann sphere, is the rest of it. Okay, so now if this condition is specified on the boundary, what you want to recover is an analytic function m in the bulk, which will satisfy this condition on the boundary. Here A, B, and C are given complex functions. And they can be arbitrary complex functions. In fact, the results that I just showed were particularly important to characterize what happens in the case of jumps. Okay, so coming back to what we have. So as a justification, another thing I would like to show as evidence is a camera. And the camera is in fact going to show at least as popularized by NASA, it's an image of the black hole and at least shadow of the black hole. And the 2020 Nobel Prize in fact went to Penrose and also Genzel and Guess for showing that a black hole is a robust prediction of general relativity. So it's a natural thing to consider. And if nature can do something so well at a large scale, compared to which I don't see any quantum computers at this scale, even theoretically, forget images of it. So yeah, at least if we understand how nature does this thing, it could help us to formulate quantum information and computing. Okay, so finally we come to light. All this correspondence is sort of given the name holography. And this is coming from a usual interpretation of holography in which you might consider two-dimensional surfaces which sort of encode a three-dimensional image. So in some sense, holography forms a physical prototype for all these bulk to boundary correspondences. And I should mention maybe that technically holography is not just this 2D to 3D image viewing thing. Even for technological purposes, it's just a general technique in which light helps us to enable reconstruction. Okay, and the main part is of this is understanding of how such a reconstruction happens requires understanding how loss happens. So the first thing to try to understand is where is all this information loss going in the first case. So we already saw that in terms of symbols and numbers, maybe even complex numbers and some theoretical tools. But how do you do it physically is the question. And loss with respect to light means you're making something invisible. Well, okay, so how do we make something invisible? If there is an object which is kept along the way of any electromagnetic radiation, then the object is going to scatter these waves. So in particular, if an observer is sitting very far away, even at some boundary of this plane, the scattering will be what kind of enables us to know that, oh, there is some object there, and that's how to perceive what is there. So what the claim is to surround this object by a certain cloak, so some sort of magic Harry Potter type cloak, and the effective result of this should be that the final scattering should actually be not should not differ at all from if there was no object at all there instead of having the object. So the only way that can happen, given that if there was an object, then there is scattering, is to not let the EM wave to even interact with the object. So there is no way the EM wave can touch the object, and that's the only way to cloak something. Is it really physically possible? Well, that's what I did as part of my thesis based on this work. In 2006, that there was a scientific breakthrough in invisibility cloaking via metamaterials. So again, metamaterials are materials which go beyond the usual kind of natural materials. And this is based on Penry, Skewering, Smith, their 2006 science article, and then Leonard also at the same time alternatively proposed a conformal technique to do this sort of mapping. So the possibility is to explore, can we actually make these light rays just bend in a way? We know that refraction does bend light waves, but can it really bend it so much that the object is not touched at all in this whole radius R1 ball? And that's what we are going to explore. So the image B is the three-dimensional sort of version. Again, so this is again a 2D image, but our eyes sort of do this holography thing automatically. We reconstruct the three-dimensional feeling of how it would be to have this thing. So the point is to not allow the waves to go inside that ball at all. And what is one thing that can help us do that? So here's just some notation for future reference in case anyone is lost after a while. Maybe the only thing, maybe the curl notation is for a cross product in case of three-component vector. Okay, so electromagnetic waves in particular are governed by Maxwell's equations. So the unknowns here are electric and magnetic fields given some parameters epsilon and mu. And there's two more equations here, which I'll state shortly. So the idea is to have such properties of the physical material such that the solutions E and H, the fields actually don't enter that region of radius R1 at all. And these properties are not really found in nature. So such materials have to be made by engineering departments. So although I have not mentioned all the names, but this was a project across departments, even material science, electrical controls, systems, and so on. Okay, so transformation optics in the general setting was what I started with, so as to enable us to look at further results in general. So I used some differential geometry and tensor calculus, in particular the Potts-Well formula, and I'm expressing Nash embedding theorem as a in red, especially because now the lift of this to the quantum case is not going to work. So people might have heard of something called MIP star is equal to RE, which says that the Cohn's embedding is false. So not all quantum systems can be sufficiently nicely embedded in certain cases. So yeah, but right now I'm free to do so. Okay, so what we are going to do is start with some Maxwell's equations in the transformed coordinates. We're just going to map this space into a new in a new space. So for example, a simple case would have been go from x, y, z, which are Cartesian, to spherical. So go to r, theta, and phi. And this is the sort of thing you can do. In fact, you can do any sort of diffeomorphism. And it turns out that the equations are still valid. This is one form of Einstein's correspondence, that if Maxwell's equations are really in the laws of nature, then it shouldn't matter who is setting up their coordinate frame in what way. So no matter what you do r theta phi, or you do x, y, z, or you do some other Poincare space, you should be able to get back the same physics. You should not be able to know that light is no longer there, or some weird thing like that. So Maxwell's equations still stay in the same formal form, but now the expression for this divergence is different. So you might have seen some weird things appearing, for example, 1 by r sine theta in the del by del theta, or if you do such a conversion or something. So all those factors that appear, the claim is that you can actually subdue them into the material parameters itself. So I will change epsilon and mu in such a way that all these extra factors that are appearing just go inside that, and that is taken into account for. And then what you're left with is your usual flat metric divergence and curl operators. So even though you are in the new coordinates, what I'm going to look at is only del by del r, del by del theta, del by del phi, nothing else. Everything else just gets consumed by the parameters. And this is the transformation that does it. So if E and H transform in this way, and epsilon and mu prime transform in that way, that's what's going to get you to this. So maybe I should give a more clear expression of this in terms of another commutative diagram. So what you have is you can start with the equations on the top left, which are in flat space. In fact, you can actually once you've done this for starting with flat space, you can do it for anything. But let's assume that you're doing it for flat space at the start. So then this is what your usual equations are. Then you can do a f, which is a diffeomorphism, changes it to these coordinates, and then the claim is that this sort of form for epsilon and mu, and this transformation, these are the pullbacks for the respective vector fields, will satisfy to make this flat enough. So we went from actually a flat space to a curved space, possibly via diffeomorphism, but then the equivalent thing is to subdue all those curves in the material itself. So now the space is itself back to flat, but the material is going to act as the metric, which is going to change the space. Okay, so understanding materials is actually understanding space in this sense. And hence, if you want to understand what a black hole is doing, or if you want to create a black hole, you don't need to actually bend space. You can just create materials and simulate it. And that's what you do. That's what I did in the labs with certain collaborators. I'll mention them later. So this is equivalent to this formulation, in which you have these two Jacobians. They are transposed in particular because that's how tensors change. And the material parameters follow this kind of diagram, which you might have seen in linear algebra. It's in fact similar to what we had in the statement. You have something and then you have its reflection. So the transpose is in some sense reflecting the entries along the diagonals. So these two are again in correspondence with each other. And there's a normalization by the determinant of the Jacobian, because that's how measures work. Okay. Any questions? That's the basic technique for how to cloak or even make up. Okay, so now everyone's ready to make these things. But what should be the transformation that we should choose? In particular, the easiest thing to do is just compress this whole ball. So let me go back to the actual physical ball. Okay, so what I'm going to do is take this as my starting space, and then have this whole thing to compress inwards towards just one point. So what happens is in this virtual space, this is just going to transform. So this whole radius R1 is going to transform into the origin, and hence it is not going to be touched at all by all these waves that are going past. I mean, they are going past. There is, technically speaking, one ray which will go exactly hit it, but that's measured zero basically. So the rest of it is not going to interact with the R1 radius at all. So for the wave, it seems like there's nothing there, but actually there is this whole thing sitting there. Okay, so that's that. Should I? Oh yeah, things. Okay, so I'm going to skip the derivations for all these diffeomorphism maps and local coordinates. And the only main thing to note here is that this map is smooth except at the origin, because there's this blow up happening. So the inverse map is what we are going to define, because we want to go from flat to this thing. So FP maps this origin to this whole ball B1, and then the rest of it just gets compressed to B2 minus B1. Okay, so in the new coordinates, you can reformulate this whole thing. And I'm going to skip all these particular derivations. But the only thing to note here is that you could regularize this whole thing in order to avoid the singularity. So you can actually have a perfectly smooth map if you just keep a delta radius ball. So don't compress it totally to the origin. Just compress it to a resolution which is lesser than the visual range or whatever minimum limit that is there. And that's good enough. That will work to make something invisible. Okay, so these are the particular parameters that you would need to actually make such a thing. And these are the regularized versions. So even for black holes, when the calculations are happening towards the singularities, these things blow up. So we use some sort of regularization always. Okay, so what about inverse problem? So if you want a unique solution to such an inverse problem that is given such a setting, can we find out what was the conductivity and permittivity throughout? So we want to know what was the metric which will determine, which in this case becomes determining the material parameters. So if there is a non-unique solution, then there is a possibility to actually have this sort of two things, whether the object is there or not, they're mapping to this same thing. In particular, for omega is equal to 0, these Maxwell's equations reduce to just the conductivity equation. So it's electrostatic case, and that's where Calderon's inverse conductivity problem is posed. I'm going to skip the rest of the phenomena because so the plan was to make Alice really disappear. So not just electromagnetic waves, but even mechanical waves and thermal waves should kind of get invisible. And there's methods to do all these things with corresponding equations. So let me skip to this table in which there is the context. So if you want to cloak something electromagnetically, you go to Maxwell's equations, you make the material parameters in such a way that the observable fields are not interacting. For thermodynamics, you go to the heat equation and look at the corresponding things. For electrostatics, there's a Navier's system of equations, and then thin plate in particular. So this was something we did for bridges. So in particular, the application is if you are able to cloak a bridge, basically no earthquake wave can do anything to it because it's no longer visible to the mechanical waves. So the bridge is basically going to stay earthquake proof. Here's experimental validation. So these are the German collaborators that we worked with, and their group actually designed the whole cloak and to the IR readings and the numerical simulations. Okay, these are particular theorems proven theoretically around this general formulation. That is in fact a trouble I experienced with extending these techniques to something called Mozart materials. So maybe I'll skip that part for now. Okay, so finally we come to this thing called Dirichlet to Neumann map and the corresponding Stecklow eigenvalues. So what you can do is define this thing called a Stecklow problem. So it satisfies the Laplacian is equal to 0 in the global bulk, and at the boundary it's proportional to itself. So lambda are the Stecklow eigenvalues. It's known that using some Sobolev space theory that these have discrete spectrum. And if M is compact, then in fact the Dirichlet to Neumann map. So you can define a map which says start with a function f at the boundary, take the harmonic extension of this in the bulk, and then take its normal derivative. Right. So it's similar to what we did before. So let me probably switch to this. And yeah, here's what we are doing. So on the boundary, you have some function which is given. You take a harmonic extension of it on the bulk. So there's some kind of bulk boundary to bulk correspondence already. Then you take its derivative and then restrict it to the boundary again. So you go from boundary here to the bulk in correspondence. And so the claim is that these eigenvalues are actually going to be very informative in the sense that first of all, the map itself is self-adjoint and non-negative definite, and their embedding gives us that you can actually use diagonalization of some sort to get these eigenfunctions, and they satisfy the variational characterization of the Rayleigh quotient. So this Stecklow spectrum, so these numbers, right? Instead of having the whole geometry of the bulk, you're only listening to the sounds or the frequencies that this shape is making. And so the plan is to recover by only listening what the bulk geometry is. So this is another form of an inverse problem in which there is a lot of loss happening. In fact, you've lost the entire manifold, but you only have the sort of spectrum there. And the results that are known is that the dimension and the boundary measure are the particular two main features that you can extract out of this spectrum. So some of the results for these are that Weinstock proved in 1954 that among all such connected planar sets with same length, the disk is what maximizes the Stecklow eigenvalue. So this is sort of a hint that, oh, there is something that can maximize these resonances based on fixing a boundary. So the boundary length is kept to be fixed, and the disk is in fact something for which the area is maximum, right? So this is sort of a hint for extremal surfaces, and it's in fact similar to what we had in case of symmetry. The maximal statement is the one which satisfies the symmetry condition, because any other statement always refers to a sub part of it. So that's that. Okay, so Brock in 2001 then extended this to all bounded domains in Rn with same volume, and the ball is exactly what maximizes the first Stecklow eigenvalue. And this was further given another upper bound by Coker. The corresponding thing, in fact, also applies for Laplacian eigenvalues. So this is a result by Lee and Yao, that you can have these conformal structures, and for the scale invariant Laplace eigenvalues, they are bounded above with equality, which is in the case if and only if the metric is actually induced by a minimal immersion M to a sphere Sn by the first eigenfunctions of this Laplace. So in fact, it tells us that all these eigenvalues are extremely special. You can get a characterization in terms of extremal surfaces, and this was finally proved in the work of Fraser and Schoen, that a compact surface M is in fact a free boundary minimal surface if and only if their coordinate functions are Stecklow eigenfunctions with eigenvalue 1. So this is the result which I will be lifting straight away from this case to quantum mechanics. So even in the case of black holes, it turns out that the same holds true. You just have to change the minimal surface to a quantum extremal surface, and that's pretty much it. Okay. So here's some asymptotic expansions that we can derive. I'm going to skip these in the interest of time. But what these do is basically the coefficients here are going to tell us exactly when or what order of layer is it possible to peek into. Because if the coefficient becomes 0, then it's going to make things invisible, right? So you may not be able to go further in that layer. Okay, so this is what enables us the reconstruction of these inhomogeneities. I shall skip the optimization as well. And okay, so finally, let me end with how to lift these things for the case of a black hole. There is again, so the rest of the slides are actually, in fact, a ditto copy. In fact, they are a hologram of the previous things. So instead of light, I have black hole. Instead of holography in terms of light, there is this concept of ADS CFT duality, which enables reconstruction. Here, CFT is a conformal field theory on the boundary, and this corresponds to something in the bulk, in particular gravity. So the idea is that, okay, so if there is this correspondence happening, then it must be that the whole bulk is being encoded in the boundary region, and this is what is called the entanglement wedge. So how is this information loss going to happen here? Because there's a d+1 dimensional thing which you have now encoded inside a d-dimensional thing. So there's always going to be a lot of extra overlaps, which is what leads to this entanglement. So how is and when is this going to be able to decode if there is an equivalence between the bulk and boundary measures? So let me introduce something called maybe this should be skipped in the interest of time. So there's something called Stirling's approximation, which you can do. And for n letter strings, so if you are communicating with bits only with symbols AB, then we can find that the number of such things because if a symbol A keeps on repeating, the order does not matter. So the regularization by n times PA factorial and n times PB factorial is accounting for that. And it turns out that this expression PA times ln PA plus PB times ln PB is exactly what Shannon defined as entropy. And the corresponding thing needs to be done for this quantum case. Okay, so this is the result by Patrick Hayden and Joza and Petz that if you get an equality of the subadditivities and the strong subadditivity, so there are classical cases for this, and the similar thing happens in the quantum case, which is done by this thing called a Petz map. So similar to what we had in the D2N map, now we are just going to transfer everything in terms of the Petz map. So let me end with a quick example of classical information theory in which if Alice is worth k bits and she goes into a black hole with n minus k bits, then the whole evolution is going to be unitary. So it's going to just be a permutation of these exponential with base 2n strings, and then Hawking radiation can be thought of as a random coding of these bits. So by classical results of capacity for erasure channel, you can recover Alice by approximately covering back just 1 plus epsilon times the original number of bits that Alice was. In the quantum case, it's the similar argument, except that you have something called the no cloning theorem. So this random encoding means that if you are able to recover Alice, the remaining black hole has to be approximately disentangled, and that's what Pascal and Hayden showed. Okay, so the particular form of Petz map is also exactly reminiscent of what we saw for the change of material parameters. Okay, so this is what my plan is to form a correspondence of all these correspondences. So it's not just holography of this d+1 dimensional ADS space, which is gravity, to the bulk, to the boundary, which is a conformal field theory, but there's this whole thing going throughout, starting from letters and language itself. Even in natural numbers and even in real complex numbers, and maybe yeah. So the rest of the talk I figured out wouldn't be within the time was to lift all these things to operators on Hilbert space and then eventually to one Neumann algebras. So the results which you saw from Goldberg-Seagal theory would now evolve to Tomita-Takesaki theory. Okay, thank you. Any questions?
Does anyone have any questions? We have time for a couple, I think.
I'm just going to state or keep on the screen this final part in case it was too quick.
I don't have a specific question, but I'm interested in some of the details that you skipped over. So would you be okay with emailing to the PGSS email your materials?
Sure. Yeah. Yes. Yeah. I'll email both the handwritten notes and the slides.